Everyone, so my name is Dima Alzain. I'm a PhD student at the Université Côte d'Azur, and today I'm going to present my work with Celia Pereira about a filter, an information retrieval filter that uses JSON agent. So let me first start to briefly state what is this. Oh, okay, I'm sorry, but it's start to briefly state what is this information retrieval filter. Briefly, it's a filter that takes into consideration the user's knowledge, and accordingly, it starts personalizing the search results. This framework has been theoretically proposed in another work 1 year ago, and the objective of this paper today is to investigate the possibility to develop such a framework in real world. To do so, we developed this framework using the JSON extension language, and we will explore together during this paper what are the advantages and the challenges to develop such a framework. The presentation outline, I will first start to describe more about this information retrieval filter. I will then move to explaining about the JSON version that we use, and I will justify why did I choose this language. Third, I will propose my framework that combines the two mentioned technologies, then move to a real case use case to finally conclude and discuss the future work. So let us start to discuss the information retrieval filter first. So this is the classical information retrieval flow. The user submits the query and the search engine returns, let's say, 10 documents. What the framework was proposing is to employ an agent that is aware about the user's knowledge. In case you're asking, how do I know what is the user knowledge? We are assuming that the content of the documents the user is reading is the content is the knowledge of the user. So whenever the user is going to read a document, the knowledge inside it will be extracted and it will be added as the agent believes. Once the agent is aware about the user knowledge, when next time the user will submit a query, the results of the search will be handled by this agent. It will compare it to what it already knows about the user and finally return the filtered result to the user, in this case, in 6 documents instead of 10. So if we want to talk more about the architecture of the agent, this agent has some beliefs, and those beliefs represent what the agent knows about the user's knowledge. Mainly, they are stated in a literal form. They include also negated facts, and they are graded because in the real world, our perception or our knowledge to many different things around us are gradual. I might be knowledgeable in computer science more than I am knowledgeable in biology. So for example, I have this agent knows that the user knows about belief A with a certainty degree of 0.4, the belief B 2, and believes that C is not true with a certainty degree of 0.9. From another side, this agent also has some knowledge rules. Those knowledge rules, they define the relationship between the beliefs. They usually have the form of A1 and A2 and etc. implies B. So the agent thinks that in case the user know about A1 and A2, then it should know also about B. In this case, in our small example, our agent thinks that if the user knows about A and B, then it will believe in X2. So X will be added to the belief space. But the question here, how will we calculate the degree of the belief X? We will discuss that in later slides. So the knowledge extraction method happens as follows. The user reads a document, the knowledge inside it is extracted. So far, we are using a method, the RAK, or Rapid Automatic Keyword Extraction. This method extracts the most important keywords and it assigns a score to each keyword. The higher the score, the more important or the more representative is this keyword of this text. And then since the beliefs should be defined as a number between 0 and 1, we are converting those keywords and those scores to beliefs and degrees using some simple normalization formula, but we will not go over it now. And then finally, we will add it to the user belief. One more aspect of this framework is that it tracks the beliefs. So whenever I want to execute the rule A and B implies X, to calculate the degree of X, I must track the relationship that links those beliefs together. To do so, we are referring to some existing work in the literature that creates justification and assigns some quality for each justification, and therefore deduce what is the degree of the belief. So if we go back to our small example, we had A and B with their related degrees. They were linked with one rule. So they were linked. We create a justification that has a quality equal to the minimum of to the maximum of both, and then it is linked to the derived belief X. So we can deduce that the degree of X will be 0.4. Now, as in real life, when we are exposed to a lot of information around us, many information could be contradictory. So I might read a document that says that the vaccine is effective and another document that says the complete opposite. The agents have to deal with such cases. We call those cases belief-based inconsistency that in our case should not be accepted in the belief base. So we follow some well-known AGM belief revision algorithm that usually prefers the beliefs having higher degrees. So in case we take a small example, the user read a document that includes the belief M, N, and C, and the user already believes in A, B, X, and not C with a certain degree of 0.9. When the agent wants to add those new beliefs to the belief set, to the existing belief set, it will notice some inconsistency between the belief C and the opposite. In this case, we compare the degrees. The degree of not belief C will have the priority to be kept in the belief base, and hence only M and N will be added and the belief C will not be added. Now comes the core of the filter. And here we want to discuss how is this agent using this information to finally filter the results. So now that the agent knows more about the user knowledge, whenever a document is proposed, the agent will compare the content of the beliefs to the content of the document. And then to do so, we created or we proposed a similarity function that takes into consideration the entrenchment degrees of the beliefs and also the existence of the negation in the beliefs and in the document to finally come up with a score that defines the similarity between the belief and the document. And then it will decide which documents and up to which similarity, up to which threshold, the documents should be returned. So now that we explained the entire information retrieval flow, the document reads, the user reads a document, we extract the knowledge inside it, we add it to the user beliefs, to the agent beliefs that already have some rules. So it does its reasoning, it tracks the beliefs and derives them, it does its reasoning for sure. So whenever next time the search engine will return some results, we will calculate the similarity with the beliefs and finally return the documents that interest the user as needed. That was the theoretical framework proposed that we already proposed in a previous part. When we decided to develop this framework, we had some conditions to find an appropriate language to develop it. One, I will briefly state what were the conditions, but mainly we wanted a language that allowed us to represent the user's knowledge and to give a degree or a grade for each belief. We also wanted an ability to revise the belief, so belief inconsistency could not be accepted. Also, update the degrees of the belief and for sure reasoning. And we found that all those conditions were satisfied by the JSON language and its extension version. I will discuss a bit about the JSON architecture and how it works for those who are not familiar. So we used the standard JSON that had an extension version that we also propose in another paper. So the JSON agent, similarly to other agents, have some beliefs. So no, first, sorry. First, it is an interpreter extended language of agent speak. It's known as an agent-oriented programming language modeled as the belief desire software architecture. And one advantage of it is that it is written and implemented in Java. It's open source, so it's easy for programmers to modify it as they want or to integrate it with their own programs. So similarly to all agents, to all agent language, this agent is allowed to have some beliefs about its environment. They are usually represented by literals. For example, this agent believes that the company one is well managed and that market stock site is a trusted website. It also allows the representation of negated facts. For example, that the company one is not international. And finally, it has annotations in which it tracks the meta information of those beliefs. In the case of JSON agent, the annotation holds only by default the source of this belief. We move then to discuss the plans of the agents, of this agent. It has the syntax. It starts by the triggering event, followed by a context and a body. The triggering event is mainly the event that will initiate the execution of the plan. It is a set of conditions, could be the addition or the deletion of beliefs or goals. But for instance, we will focus on beliefs. Once the plan is triggered, we will check if the context is valid. The context in this case is a set of conditions also. In case the triggering event and the context are satisfied, then the actions in the body will be executed. So if we show a small example, we have the first part is the triggering event, followed by the context, and in case it is satisfied, the body, good to buy, will be executed. So now I will talk more about the version of JSON that we used. It has also proposed like 1 year ago, in which the main features were that it allowed the concept of graded beliefs. So beliefs were assigned some grades. It allowed the representation of knowledge rules, and it had some belief revision functions. We start by discussing the gradual beliefs. This extension of JSON assigned to every belief a certainty degree in a way that it represents the degree to which the agent believes this fact is true. And it ranges between 0 and 1, and it is tracked in the annotation. So in this example, well managed of company 1, we could also track in the annotation part the certainty degree 0.5, let's say, for the first belief, and 0.8 for the second belief. The second feature that is also special about this extension is that it allows the representation of knowledge rules. Knowledge rules that usually have the form of A and B imply C that we already discussed before. So this extension proposed a new syntax to represent those rules. Mainly, it should start with reserved word TEI that we call the trigger event independent. So the advantage of this is that we can represent the rule using just one plan, because just to mention, and those who work with JSON, they already know that in case we wanted to represent this rule in the previous version, we had to state at least two rules. But now with the new version, only one rule can represent the plan. It's also one more advantage is that it executes all the applicable plans. Also, for those who work with JSON know that in case several plans have the same triggering event, only the first one will be executed and the other one will be ignored. And this is not what we are aiming to when we want to represent knowledge rules. So in this case, both rules are applicable and both of them will be executed. Finally, we move to the last special feature of this extension is that it allows belief revision and belief reasoning. Similarly to the information retrieval framework that we already proposed, it also doesn't allow the belief inconsistency. So whenever there is an inconsistency, it relies on the degrees of the beliefs to decide which one has to stay. And it also tracks the belief using the same algorithm that were used before. So those, I think those were enough justification and motivation of why we decided to use JSON for this framework. Now I will propose and I will explain how did we develop this framework. First, we want just to make sure that the terminology is unified. We use the JSON agent. In the JSON agent, we use the beliefs to represent the agent belief about the user's knowledge, also its initial beliefs, its extracted beliefs, which means the knowledge extracted from the text document, and the derived beliefs. The certainty degree corresponds to the entrenchment degree in the information retrieval framework. And finally, the plans of JSON were used to represent the knowledge rule in the information retrieval framework. This is the belief revision operator that we adopted. Briefly, this belief revision operator also relies on the degree of the belief. So whenever a new belief arrives, it will first check if it already exists in the belief base. If it doesn't exist, then no problem, it will be just added. If it already exists, then it will compare the degree of the existing belief to the degree of the new belief. And then the belief with the higher degree will have the preference to stay. And as stated before, JSON is open source and is written in Java, which was very practical to develop. So we developed the information retrieval filter. We integrated it with the extended version of JSON for sure using Java. The chosen search engine was Lucene, that was also open source. And just to note that we use the standard analyzer for both indexing and search. The setup was set to return 10 documents, just to simplify the example for this presentation. And the objective was to return documents that contain new information in respect to the user knowledge. And we selected one topic of a public BBC article that was technology. So I will, maybe it will be easier to relate with the real world with this use case. So in this use case, we assume that the agent just started its interaction with the user. So far, it doesn't know anything about the user's knowledge. So as we see, the beliefs are empty. It has only one plan that says, in case the user knows about PSP and about Gizmondo store, then it knows also about the Sony Corporation, which is logical because Sony is the one that created PSP and Sony is also the owner of Gizmondo. So in case a user knows about both, then it's logical that it knows about its mother company. So we start the user agent interaction by issuing a query, gaming device. This query was submitted to Lucene and Lucene returned those documents. Since the agent doesn't have yet any knowledge of any information about the user knowledge, then all the 10 documents were returned to the user. And this is where the agent will start building its knowledge about its user. So those were the documents returned to the user. We assume that the user selected the first document to read. What happens is that the knowledge inside of this text document will be extracted using the RAC method. For this document, 39 keywords were extracted. We show only a sample. In the first column, we see the RAC score, and next to it, we see the belief degree. And as we see, it is a number between 0 and 1. And those degrees with their beliefs are added to the belief base. Now it's time for the agent to start its reasoning process and check if some of the documents or some of the plans are applicable. In this case, we can see that the user has PSP and has Gizmondo in its belief base. So the agent will execute its reasoning process to derive the belief SONY. Using the belief revision and the belief tracking algorithm that we discussed before, we track the relation between Gizmondo store and PSP with the justification. This justification will also link to the derived belief that is SONY. And now we know what is the degree or up to which extent the user is knowledgeable about SONY. In this case, it's 0.1. The next interaction is that the user will submit another query that is the PSP. We see on the left the 10 documents returned by Lucy. And you will notice that not all those 10 documents were returned to the user because the agent actually filtered them. So the agent extracted the content of every text document of those 10, and it compared it to its beliefs about the user's knowledge. And apparently it excluded 2 documents from the list of 10. And so on. So whenever the user will submit a query, the agent will filter it, will return some document, then the user will select some documents to read, it will extract the knowledge, do the revision, and it's the building process. So we come to the end of our presentation. To conclude, we presented a new way of usage for BDI agents in information retrieval, where the beliefs of BDI agent, or in our case, JSON, were representing the user's knowledge. They were gradual, and we could successfully revise the belief. This gives opportunity for other researchers who want to apply this methodology or this architecture to other tasks requiring personalization. And finally, we want to discuss the future work and the challenges of developing such a framework. First is the extraction of negated keywords. So the framework has, theoretically, it represents the negated facts, but actually it is still a challenging task to extract negations from non-structured texts. So once this challenge will be unlocked, it will be easier for us to perform real belief revision. In this case, we will really detect if the user has 2 contradictory beliefs. And finally, we would like also to take into consideration the synonyms and the similar words in order to reduce the size of the belief base and make it more efficient. So that's it. I hope you believe in this contribution. And in case you have any questions, do not hesitate to contact us.